Hi, everybody. I'm William, and today I'm going to be talking to you about pseudodistributions and the derandomization of space-bounded computation. Recall that BP space S is the class of languages that can be decided by randomized algorithms that use O of S bits of space. The popular conjecture is that BP space S coincides with deterministic space S. So in other words, this conjecture is saying randomness is not necessary for space-efficient computation, so you might as well throw all your fair coins into the trash can. To try to prove a conjecture like this, we would like to understand what is this algorithm doing as a function of its random bits. And the first observation is that when we fix the input and we look at the function of the random bits, that function can be computed by a model of computation called a bounded width read-once branching program. So this model of a read-once branching program is a directed graph where the vertices are arranged in n+1 layers. N is called the length of the program, and then the width of the program is the number of vertices in each layer. Each vertex has two outgoing edges pointing to the next layer of the program, and the two outgoing edges are labeled 0 and 1. A program like this can process an input string by starting at a designated start vertex in layer 0, and then reading the input string from left to right one bit at a time and arriving at some vertex in the final layer. The program either accepts or rejects depending on whether it arrives at a designated accept vertex in that final layer, and in this way the program computes some Boolean function f on n bits. The traditional approach to derandomizing space-bounded computation is to try to design a pseudorandom generator for this model. A pseudorandom generator is a function that stretches a short, truly random seed out to a long pseudorandom string. In our context, what that means is that for every polynomial width read-once branching program, the expectation of the program is essentially the same up to some small error epsilon, whether we plug in truly random bits or we plug in pseudorandom bits from the generator. Now, if we could design a log space computable pseudorandom generator for this model with the optimal seed length, which is log n over epsilon, that would immediately imply a full derandomization of space-bounded computation. And in particular, it would imply L equals BPL. So far, we're not there yet, though. The state of the art is that there's this construction by Nissan from 3 decades ago with seed length log squared n plus log 1 over epsilon times log n. So it's quadratically worse than what we want. There's been a lot of effort trying to improve Nissan's generator, and there's been success in special cases. But for fooling polynomial width read-once branching programs, it's a stubborn problem. It seems to be very difficult to design better pseudorandom generators. And so that makes us stop and think, it's not like there's some law that says if you want to derandomize an algorithm, you have to use a pseudorandom generator, right? So maybe we should be thinking outside the box a little bit. And we should be trying to derandomize without necessarily designing better pseudorandom generators. And in particular, this motivates us to consider some relaxations of the concept of pseudorandom generators that are hopefully easier to construct. So today I'm going to be talking to you about one particular generalization of the concept of a pseudorandom generator, something called a weighted pseudorandom generator, which is a concept that was introduced a couple of years ago by Braverman, Cohen, and Garg. The definition is we have a pair now, G comma rho. G is still this function that maps R bits to N bits. And now rho is a function that assigns a real weight to each seed. The requirement is that for every polynomial width read-once branching program, F, the expectation of the program is essentially the same up to some small error epsilon in 2 scenarios. The first scenario is still we plug in truly random bits. The second scenario now is we pick a random seed, plug that into G to stretch it out and feed that into the program F, and then multiply by the weight of that seed. So the key thing to keep in mind is that these weights are allowed to be negative. So that opens the door for the possibility that if we orchestrate things just right, maybe we can have some error cancellation. That's the motivating idea behind this definition of a weighted pseudorandom generator. One can show that weighted pseudorandom generators are intermediate between pseudorandom generators and another concept called hitting set generators, which is a standard one-sided version of a pseudorandom generator. If we could design an explicit optimal weighted pseudorandom generator for polynomial width read-once branching programs, then that would imply a full derandomization of space-bounded computation, just like if we had a true pseudorandom generator. Weighted pseudorandom generators are also known as pseudorandom pseudodistribution generators, which is based on just this slightly different formalism and way of thinking about these things. For today's purposes, a pseudodistribution is a real linear combination of n-bit strings. So we have these n-bit strings, these zi's, and then each one has a real coefficient ai attached to it, which is called a pseudo probability. This is a generalization of the standard concept of a probability distribution, which would further require that the AIs are between 0 and 1 and that they add up to 1. We can also generalize other concepts from probability theory. For example, we define the pseudo expectation of a function under some pseudo distribution by taking the corresponding linear combination of the outputs of that function. In these terms, our goal is to design an explicit pseudo distribution such that for every polynomial width read-once branching program, the pseudo expectation of the program is essentially the same as the actual expectation of the branching program under a truly random input. We would like our pseudo distribution to be sparse because we want the corresponding weighted pseudorandom generator to have a short seed length. So I think these ideas are intriguing, but the most interesting thing is that we can get constructions of these objects. Like I mentioned before, the state of the art for actual pseudorandom generators is Nissan's generator, which has seed length log squared n plus log n times log 1 over epsilon. When Braverman, Cohen, and Garg introduced the concept of a weighted pseudorandom generator, they gave a construction with this improved seed length, O tilde log squared n plus log 1 over epsilon. Okay, so they got rid of one of the factors of log n, and that means that their generator is better when the error parameter epsilon is very small, like maybe inverse quasi-polynomial. Now, admittedly, we would have preferred to improve the log squared n term in Nissan's generator's seed length. That's the more important term. But still, I mean, it had been several decades with no improvements. So, I mean, an improvement in any regime of parameters is exciting and interesting. Unfortunately, Braverman, Cohen, and Garg's construction and analysis were pretty complicated, which motivated researchers to try to look for simpler constructions. And at this point, there have been several follow-up papers that are getting simpler constructions of essentially the same phenomenon. And one of the benefits of these simpler constructions is that we're able to get rid of some of these log-log factors that were present in Braverman, Cohen, and Garg's original work. And so at this point, we have explicit weighted pseudorandom generators for polynomial width read-once branching programs with seed length O of log squared n plus log 1 over epsilon. And this is the main theorem in the paper, and it's the main theorem that I want to tell you about today. I do want to also quickly mention another theorem that's in the paper, because I think it helps to motivate this whole line of work. The other theorem that's in the paper is an application. It's a better unconditional derandomization of space-bounded computation. Since the 90s, the best unconditional derandomization has been this theorem by Sachs and Joe, which says that BP space S can be derandomized in space S to the 3/2. Today, we can slightly improve this bound by shaving off a factor of square root log S. Okay, so the new bound is S to the 3/2 over square root log S. So it's a very slight improvement. The proof of this theorem uses like Sachs and Joe's approach and then combines that with some of this recent work on weighted pseudorandom generators. And I want to emphasize that actually for this application, it's sufficient to use recent prior results on weighted pseudorandom generators. It's not actually necessary to use this last improved construction of weighted pseudorandom generators. That's the main theorem in this paper. I want to also point out just something amusing about this timeline here. If you focus on the problem of derandomizing RL, right, these are algorithms with one-sided error, then the first derandomization is just Savage's theorem, which already implies that RL can be derandomized in space log squared n. And then 26 years after Savage's theorem, Sachs and Joe presented their algorithm with this improved bound of log to the 3/2 n. And now, 26 years after Sachs and Joe's algorithm, we have this, this slightly improved bound. We can shave off this factor of square root log n. So it's 26 years in both cases. So I say this just because I'm hoping that it will be fewer than 26 years before our next improvement. Hopefully, we can derandomize RL sooner than the year 2047. But, we'll see. Okay, so for the rest of the presentation, I'd like to tell you about the construction and the analysis of our improved weighted pseudorandom generator. Okay, so recall the goal is we want a weighted pseudorandom generator for polynomial width read-once branching programs with seed length O of log squared n plus log 1 over epsilon. And the interesting thing here is the optimal dependence on epsilon. For the first step of the construction, though, we're actually going to be more focused on the dependence on n, the size of the branching program. So the first step of the construction is this lemma, which says that there's a family of pseudorandom generators. So we have G sub x for each x. And each generator in the family has seed length O of log n. So it has this excellent dependence on n. Okay. Now, the caveat is that these generators, they only work on average in some sense. Or to be more precise, for every polynomial with read-once branching program, f, all we can say is that most generators in the family work for that particular branching program, f. Or actually, in more detail, if we pick x at random, so we're sampling a random generator from the family, then with very high probability, except with this tiny failure probability epsilon, that's like the inverse quasi-polynomial error or whatever that we're shooting for in the end. With very high probability, the generator G sub x fools that branching program f and all of its subprograms for that matter with this moderate error, like inverse polynomial error. Okay, and then we also need a bound on the description length. This string x that specifies which generator in the family we're dealing with has length O of log squared n plus log 1 over epsilon. Okay, now, I should mention that this lemma is not particularly novel. Very similar ideas have been used in prior works on space-bounded derandomization. And the construction that proves this lemma, the family of pseudorandom generators, is it's a pretty standard trick. What you do is you take Nissan's generator, G, and you compose it with something called a sampler. For those of you who need a reminder, here's the definition of a sampler. So roughly speaking, the definition says that for any test function t, the sampler samples inputs to t in a way that approximately preserves the expectation of t. And the key thing about a sampler, the thing that makes it useful, is that it has these two inputs. The second input of the sampler is short, and the first input of the sampler is good with high probability. Okay, so if you just plug in this definition, it's pretty much immediate to prove that this family of generators has the property that I claimed that it has on the previous slide, right? Because for any fixed branching program f, you can look at the test function that takes a seed and plugs it into Nissan's generator and then plugs that into the branching program. And if we take a union bound over all subprograms, then that finishes the proof. And then if we have great constructions of samplers. So if you just plug in a good construction of samplers, then you'll get the parameters that I claimed on the previous slide. So that's the end of this first step in the construction of our weighted pseudorandom generator. Okay, so where we're at so far is that, okay, we have this branching program f that we'd like to fool, and we can pick a random x to sample a generator in the family, and with very high probability, we'll get a generator that works for that particular branching program, right? We have this moderate error pseudorandom generator G sub x, which has seed length log n, which is great, and it fools f and all of its subprograms with this moderate error inverse polynomial in n. And what we'd like to do next is we're going to perform certain operations on this generator G sub x to decrease the error, so that we decrease the error down from inverse polynomial all the way down to epsilon. And this process of decreasing the error was actually done already in prior work. It was done by Cohen, Duran, Renard, Sperlo, and Toshma, and independently by Pine and Vedant. Okay, and as you'll see, when we perform these operations, there are going to be some minus signs that show up along the way. And so that's why what we end up with at the end of the day is a weighted pseudorandom generator instead of a traditional pseudorandom generator. So let me explain what these operations are. The operations are best understood as operations on pseudodistributions. Okay, well, if we have two pseudodistributions, of course, we can take a linear combination of pseudodistributions, right? Because a pseudodistribution is itself a linear combination. And of course, you can take a linear combination of linear combinations. Okay, and then the other operation is a tensor product. If you want to take the tensor product of two pseudodistributions, you do the double sum and then you multiply the pseudo probabilities and you concatenate the strings. Okay, so in terms of these operations, here's our construction of a low error pseudo distribution. All right, so we start with this moderate error pseudo-random distribution D, right? This is the distribution that's sampled by the generator G sub x. then D prime is given by just this formula. And I mean, I'm just putting the formula here so you can see that it's extremely explicit. Don't worry about the details of this formula. But just at a high level, this formula says that D prime, our low error pseudo distribution, is given by D plus a bunch of correction terms, M correction terms. M here is an accuracy parameter where larger M is going to mean lower error. In particular, we claim that if you pick M to be roughly log 1 over epsilon over log n, then this pseudo distribution D prime fools our branching program F to within error epsilon. So the proof of this claim uses this neat connection between derandomizing space-bounded computation and inverting Laplacian matrices, which was a connection that was identified by Ahmadinejad, Kellner, Murtaugh, Peebles, Sidford, and Vedant. So let me explain how it works. So we've got our branching program F with capital N many vertices. Let's let P be the matrix of all the expectations of the subprograms of F. Okay, and then P hat is the approximation to P that you get using our moderate error pseudorandom distribution D. Okay, so one entry of P hat is the expectation of a subprogram under this moderate error pseudorandom distribution D. Okay, and then let's define W to be the random walk matrix of F. That is, one entry of W tells the probability of going from one vertex to another if you take a single random step. So each entry is just 0 or a half or 1. And the neat thing is that there is a formula for P in terms of W. P is given by the sum of all the powers of W, basically because W to the I is giving us information about length I random walks, or in other words, it's giving us information about length I subprograms. Now this is a geometric sum, and so we can simplify the formula and say that P is the inverse of the Laplacian matrix I minus W. Okay. Now, this is a very neat observation, and for today's purposes, the reason that it's useful is that this suggests an alternative way of quantifying the error of our approximation matrix, P hat. Okay, the simplest thing to do is just look at the entry-wise error. Okay, and entry-wise, P hat is close to P to within error inverse polynomial. But now that we know that P is the inverse of the Laplacian matrix, that motivates us to say, all right, well, let's look at the errors after multiplying by the Laplacian matrix. Okay, so we define E, our error matrix, to be the identity minus P hat times the Laplacian. This error matrix E turns out to be the key to analyzing the pseudo distribution D prime that I defined previously. Here's how it works. We define a new matrix, P double hat. It's going to be a new approximation matrix to P. We define it by this formula that says it's P hat plus a bunch of correction terms. The correction terms are the powers of E up to E to the M times P hat. Okay. Now, if you just work through the definitions, you can show that this matrix P double hat contains, just as one of its entries, this pseudo expectation of our branching program under our pseudo distribution D prime. Okay, so that means that the question now becomes, how good of an approximation matrix is P double hat? Okay, and like before, let's measure the errors after multiplying by the Laplacian matrix. Okay, so as a reminder, when you take P hat and you multiply it by the Laplacian matrix, you get the identity minus E. That's how E was defined. Okay, so that means that if you take P double hat and you multiply it by the Laplacian, then you get, just plugging in, you get this big old sum, but it's a telescoping sum. Everything but the outer two terms cancels, and we end up with the identity minus E to the M plus 1. So effectively what's happened is that we've taken our error matrix E and we raised it to some high power, which of course means that we are decreasing the errors. And in fact, what one can show is that, for the value of M that we set, like log 1 over epsilon over log n, this matrix P double hat has entry-wise error at most epsilon. And so that implies that this pseudo distribution D prime fools our branching program F to within error epsilon, just like we wanted. Okay, so that completes the analysis of our weighted pseudorandom generator. And you can double check that it has the seed length that I claimed. Okay, so here are a few open problems, just in case you're interested. And please feel free to contact me if you have any questions or comments about this work. And otherwise, thanks for watching.